Many thanks, Cliff. Those of you who were here for the verified software bridging workshop 3, so the third workshop, which was just a few weeks ago, will know just how important this topic is, how close it is to my heart, how much I really care about it. I am so excited about this program. I can't wait for it to come to INI, and I am just so delighted that these bridging workshops are happening in the interim, just to tease us on our way as an exciting appetizer for the main program. It's going to be very exciting. This is, again, particularly delightful for me because some of you already know that this afternoon's event, particularly for me, because some of you might know that Tony is my academic great-grandfather. So it is lovely for me to be part of this event and to open the workshop. I'm very much aware of time and that we need to possibly have some logistics about who exactly is the first speaker. So just to say, can't wait to have those of you who can come to the main program. It's going to be amazing. Thank you to Shankar for all the organising. Thank you to Cliff for huge amounts of preparation that's gone into this workshop. And I might have to duck out at some point for logistical reasons, but I will be back on also for the final session. So can't wait to see you all later on, and over to you.
Thank you very much. So for those of you who don't know me, I'm Cliff Jones from Newcastle University. It's my honour to chair today's programme, which is devoted to one of Tony's early contributions to computing science. Written in Algol 60, algorithms 64 and 65 were published in Communications of the ACM 60 years ago. These were followed by a longer explanatory article in BCS Computer Journal a year later in 62. Tony returned to the algorithms as examples for his later papers on verification, but others found plenty of meat in the original algorithm. Although modest by Tony's standards, over 1,500 citations are recorded in Google Scholar to Quicksort. Perhaps more important measure, and it would be interesting to come up with an estimate of it, is the number of hardware hours which have been run executing Quicksort over the time. Perhaps we'll come back to that later. Housekeeping, one normally has to talk about fire exits. If you get a fire your end, that's your problem. We are recording. If you don't wish to appear on the recording, you should stop your camera and post any questions in the chat rather than speak them. I'll occasionally mute and even cancel video during the talks, and you might want to do the same so that you don't pick up background noises. There is a live transcript facility, which for some strange reason defaults to on for some people and off for others. If you want to get rid of it, the CC button at the bottom of the screen toggles that. We have 3 talks of 20 to 25 minutes this afternoon. We'll stick to schedule, so the longer the speaker speaks, the shorter the discussion. But there will be a final session which gives participants and speakers a chance to ask Tony questions or vice versa, however it goes. Now, I was going to say the first talk is by Doug McIlroy. Has Doug arrived? No. The first talk is by Bob Sedgewick from Princeton. Bob is the founding chair and William O. Baker Professor in the Department of Computer Science at Princeton. His research expertise is in algorithm science, data structures, and analytic combinatorics. He's the author of 20 books, many of which have been used for decades as textbooks and reference works. Bob, with thanks for stepping in, over to you.
Okay, let me get my screen going. Okay, is my title slide showing?
Yes.
Okay, so actually my talk is a bit of a survey, so it fits well as the first talk. So I'm going to talk a little bit about what we know about Quicksort. As we know, Tony invented it in '59, and he wrote a definitive paper on it in '61, where '62 was published. When I got to Quicksort, when I got to Stanford, I met with Don Knuth. And one of the things that I had done, his book had just come out, and I found a way to improve his implementation of Quicksort, which made him rip out 10, 15 pages of his book. He was very unhappy about that. But he said that he thought there was maybe one good thesis left in Quicksort. And I don't know if it's good, but at least that was my thesis. And then I wrote a couple of papers after the thesis, and actually I got this review. I hope this is the last paper we see about Quicksort. I always fantasized that maybe it was Tony Hoare who wrote that, but anyway, it got my attention. And I didn't write another paper about Quicksort for about 20 years. I figured I got tenure, became full professor, got to Princeton, chair at Princeton, then it's pretty safe to write another paper about Quicksort. Actually, there have been many, many papers written about Quicksort, and I'm going to talk about some of the important results and the facts that we've learned about Quicksort since the 1960s. So one of the first ones is that really it's worthwhile to read that original paper, and I'll go into some detail about why I think that's true. One thing that we've learned is that you have to be really careful about randomizing. And there's several stories about the dangers of not being careful with randomizing. I'll talk about that. And really the most important practical thing I think that we learned is careful attention has to be paid to equal keys in a library sort. One thing we've learned is that Quicksort is optimal in a very important and strict technical sense. There's a common key type that we can really improve the original implementation substantially. I'll talk about that. A lot of probabilists have studied the limiting distribution of Quicksort. And what we know is that it's not normal and it's pretty difficult to characterize. Later on, Sebastian will talk about multi-way partitioning, which is very effective, or at least effective on modern machines. So that'll be the next talk or the one after. And the most important thing is Quicksort remains the method of choice. I don't know if you want to talk about the number of machine cycles that it is, but certainly it exists on billions of devices now. So every device has it. So that's definitely an important fact about Quicksort. Okay, so I'll go through these and spend a few minutes on each one in this talk. Okay, so why should students read Hoare's paper? Well, it's an example of what I've been calling lately algorithm science. So what is algorithm science? Quite simply, it's the idea that we should be applying the scientific method to the design and analysis of algorithms. That means create some sort of mathematical model, use that to develop some hypotheses about what happens in the real world, then run some experiments to validate those hypotheses, and then iterate on the basis of facts learned or adjust parameters. It's quite natural when explained this way. Then I just want to point out that there's a lot of theory of algorithms around that is really not algorithm science. This is just a little diagram of it. So let's say it starts with Knuth, who showed us that really was possible to create really accurate mathematical models. And he even focuses on exact formulas. And then very early on, A.O. Upcroft and Ullman, and then later Corman, Leifson, Revest, and Stein went more into the theory of algorithms, or sometimes people call it computational complexity, but really deals with upper and lower bounds on performance and trying to make them match. And that did lead to a golden age of algorithm design for many, many algorithms. But it's not the same as being able to validate performance on real computers. And so it's another branch away from Canute. And I put it as a branch away because nowadays where we really focus on getting good approximate answers in order of growth. And I'll give an example of what I mean. So the theory of algorithms, what everyone's used to is you say, well, the running time is big O of n log n. Actually, Quicksort, the running time is big O of n squared because that's the worst case. But anyway, this statement is really not usable for developing hypotheses about what happens on a real computer. So what we like to say instead is that use the tilde notation. It says as n gets large, the running time grows with some constant times n log n for some particular constant. So that's what I call algorithm science. With statements like that, we can make specific predictions about what happens in the real world. And what would I use it as an example of that? Well, it would be Hoare's paper. So just to make it so I can tell this story in 5 minutes, I've taken a little bit license with what he actually said. But basically what the paper says is the running time of Quicksort for n random inputs is grows with a constant times n log n, where c is a machine dependent constant. Very explicit about that. And if you want to make it run faster, you can work on lowering c. And talks about different ways of doing that. So nowadays, what we would say is you can actually create a hypothesis about what's going to happen in the real world from that statement. And that is specifically doubling n will increase the running time by a specific factor. And that's a really easy proof. What happens is the constant goes away when in this process. So now it's not machine dependent anymore, this statement. The running time is going to increase by a factor of 2 and decreasing as n increases. And there's data, there's experiments in Hoare's original paper that validates this. So he tells us he implemented and ran the thing for these values of n. And these are the running times. I guess they're in seconds. And if you take the ratios, it's a little more than a factor of 2. And as n increases, it gets close to validating this hypothesis. And this is really amazing for a paper from 1961. You can run and validate this hypothesis today, and people have done it on thousands of computers ever since. It is a very specific statement about the performance of this algorithm that can help people wanting to know what's going to happen in the real world. And that's what we'd like to see for many, many more algorithms. So I have students read this paper. This is what they should be doing when analyzing algorithms. Now, it depends on some things, and this is a segue into the next topic. This analysis does assume that the partitioning element for Quicksort is chosen at random. It assumes that the keys are distinct, or at least the effect of equal keys is negligible. And the main thing it assumes is that after you're done with partitioning, the two subfiles are randomly ordered. This is a so-called dots diagram of just the values of the elements in the array as it moves left to right. So a sorted array would have the dots on the diagonal. And below is after partitioning, there's one element that's in position, and then everything smaller is on its left and everything larger is on its right. And you can see those two subarrays are randomly ordered. They're little microcosms of the original problem, and that's what makes it possible to analyze it. And there are some early horror stories that were problematic when people didn't pay attention to that. So one famous one, also in Canute's book, is a clever idea for partitioning on the median of 3 that was trying to save, I think, one comparison, but actually wound up with quadratic performance because the subfiles weren't random. Another idea that people try is, well, it's annoying to actually keep track of that partitioning element. Why not just pick a random value and partition on that? And the problem with that one is that you don't have random subfiles, and it actually does negatively impact the performance. One of the early problems that we had was convincing software developers to use randomization. That they're very they avoid randomization because they want to be able to test and maintain their software. And it's annoying and difficult to do that if the input is different every time. So we kindly reached a standoff finally and say, okay, just randomly permute the input before the sort, then you can separate out the randomization from the algorithm. But that's not the real practical problem with this. The bigger problem is that in real applications, the keys are not necessarily distinct. I wish we had all noticed that earlier. Well, I noticed it pretty early, but people didn't pay attention. So what happens is that you're going to get quadratic performance. And actually in many implementations, if they pay no attention to equal keys, what will happen is the quicksort partition will just put one element in place and then be left with the remaining n-1, which immediately gives quadratic performance. I think the original paper maybe even has that flaw. So I studied that in my thesis, and there are two easy fixes. So the trivial one is to stop the pointers on equal keys and exchange two equal keys if necessary. And that brings the worst case performance down to n log n and is trivial to implement. Another thing to do is to just collect all the equal keys together and put them in place. And in 1970s, I didn't think that was worth the trouble because the other one's so trivial to implement. So this is just a diagram showing on the left, the bars are random. In the middle, it's been partitioned on one value. There's a lot of equal keys. And you can see it gets the job done in a relatively small number of steps. So Bentley and McIlroy, and when McIlroy comes, he can explain it, came up with, what happened was a user came and tried to use the library Quicksort to sort binary data. It was just zeros, and keys were just zeros and ones. And it was quadratic. So they didn't pay, the implementers of Quicksort didn't pay attention to the original idea to stop pointers on equal keys, and it just went quadratic. If there's a lot of equal keys, even if there's only one value that appears a lot and the rest of it's random, eventually you're going to sort down to have a large file of all equal keys to deal with, and it goes quadratic. So Bentley and McIlroy figured out an elegant way to implement three-way partitioning that just uses n-1 compares, doesn't cost too much if there are extra equal keys. And my implementation only added 4 lines of code to Quicksort. And this one is still in use today. It's what you find in Java and many others. And when you think about it, modern applications, records have all kinds of fields, and a lot of times the fields have a small number of values, like dates or male or female, where there's going to be a large number of equal ones. And of course, users of just say, sort me on that field, and you need to have this three-way partitioning for sure. And when working with Bentley and implementations of this for the 3rd edition of my book, we realized that actually Quicksort is optimal in a specific technical sense. So this is just a little map to state the results. So if you have small n different values and you have their multiplicities, and we're going to assume that they're randomly ordered and they use three-way partitioning. The average number of compares, well, there's an easy lower bound from information theory. And I won't go through the proof of that, but it's a standard information theory lower bound in terms of the compares remove entropy, and that's a lower bound on the number of compares. Where the standard entropy function pi log pi and the number of compares taken by Quicksort with three-way partitioning has got to be at least that expression in H minus n. In my thesis, I actually just easily adopted a proof by Burge that showed that the exact number of compares for Quicksort in this scenario is given by this expression here. And then Bentley and I realized that actually, without too much work, you can prove that this Q function is less than the entropy function times log 2. So that is the average number of compares is within a constant factor of optimal, where the constant is 2 natural log 2. So no matter what the multiplicities are, no method can use fewer compares. And Sebastian proved a conjecture, well, it's based on a well-known assumption that with sampling, we can get the constant to approach 1. So Quicksort is optimal in a very specific technical sense. As people think of Quicksort as not being optimal because it has an extra 1.44% number of compares compared to optimal sorting algorithms, but really you're not going to get fewer compares than Quicksort. So that's something that we learned in the 90s. And another thing related to this is there's a very common key type, and that's when the keys are strings, when they're sequences of characters. And when we take three-way partitioning as a primitive, we get what's called three-way string quicksort. And what we do is we just look at the first character of each key and do three-way partitioning, and then put everything equal to every string that first character is equal to the partitioning element into position. And then we get 3 subfiles, one with the first character less, one with all equal, and the other with first character greater. And then for the middle, you don't use the first character anymore. And this is a really simple algorithm that really writes itself, and it cuts down the number of compares to just character compares, not full string compares. And that was a lot more work for some colleagues, and that was also been proven optimal in a specific technical sense. And it's faster practically in practical sense than other algorithms for sorting strings. And the other thing, maybe even more important, is ternary search trees, which is the duality between quicksort and binary search trees. This algorithm comes into ternary search trees, where build a search tree and do a three-way branching based on the characters and have one for everything that's equal to the first character, one for less, one for greater. It's a very simple search algorithm for strings that really writes itself. And it's actually faster than hashing in practical implementations because it doesn't need to examine the whole string, just the characters that differentiate the strings. So that's another important fact that we learn about Quicksort. And then the other one is about the limiting distribution. This is when we got probabilists involved in our community for analyzing algorithms. The question is, what is the limiting distribution of the number of compares for Quicksort? This is just computed precisely for just n up to 50 or something, normalized to be between 0 and 1. And it looks like it comes to a limit. So it didn't even know if it exists at first. And after a while, a student in France proved that If the limiting distribution exists, it's not normal. And that was a surprise. We thought maybe it was normal at first, although from this design, it doesn't really look like it's quite going to normal. The left tail decreases much faster than the right tail. Then a few years later, Mireille-Régnier showed that it exists and therefore it's not normal. And then Rossler showed, and this uses martingale theory. So if you want to understand these results, you need to study some probability. So it's a unique fixed point of an explicit distributional identity. And then a lot of people were able to use that to study the rate of decay of the tails. And there's many papers on that. And here's just an example of recent tail bounds by Svante Janssen. And so the left tail decays doubly exponentially, and the right tail just a little faster than exponentially. And that's about what we know about characterizing the limiting distribution. So there's a lot of research, quite a few papers behind these results, and probabilists are always interested in new distributions. And Quicksort is important. It's important as Quicksort, but it's also important because it's the external path length of binary search trees. And there's lots of types of trees people want to understand distribution of external path length. And this seems to be like the core problem to be studied. So that's my summary of what we've learned about Quicksort. Read Hoare's paper, pay attention to randomization, pay a lot of attention to equal keys. You're not going to do better than Quicksort, and definitely string sorting is important. And there's still plenty of advanced math to do in the study of Quicksort. And systems programmers are still excited about it because they find ways to change it and adapt to modern machines. And Sebastian will talk about that. And it's still the method of choice. So, wow, exactly on time. So I'm happy with that. Thank you.
Yeah, thank you very much, Bob. Beautiful talk and beautifully timed. Thank you very much. Questions? Perhaps you could raise the virtual hand rather than all jump in.
You got to stop my share. Okay, there we go.
Warren, you're muted, but please ask.
So thanks for the talk. I wonder about, memory hierarchy and the unequal distribution of the response of memory, in other words, caches, especially multi-level caches, and whether there's been any, study about that as it concerns these algorithms. Of course, getting things partitioned small puts them in the cache, but I'm just curious if you have a comment about that.
I'm wondering if Sebastian hired you as the stooge to set up his talk, because it's good that you're wondering, because you're going to hear a lot of detail on that from Sebastian. And it's definitely an important consideration. And a lot of people have studied it, and there've been really interesting and surprising research results that have led to state-of-the-art sorting for the 21st century.
Beautiful non-answer, so thank you. I'll listen to the next talk.
Yeah, next talk. Yeah.
I'll ask another one though, since nobody else has asked. I mean, it seems that it took 10 years to kind of, at least, and maybe more, to kind of, I'll say, analyze Quicksort. And I mean, on the surface, it looks pretty simple, but do you have any comment as to, why that is, and, what the energy was required behind all of that? I mean, it's kind of, I mean, if it's that hard to scrape out the goods out of, 10 or 12 lines of code, I can't imagine that what we're going to do for 100 lines or 1,000. I mean, that's just a, just an emotional question, really. But
yeah, I have a couple of responses to that. First of all, Hoare got it analyzed in his paper. In fact, he seemed to think it was so trivial he didn't even show how. The years of development is really coping with the types of questions that you're talking about what can we do to simplify this process. And one of the points that I want to make is that going to the theory of algorithms, just working with big O worst case analyses is simple.
thanks.
Go ahead, Tony.
Yes, just a correction and attribution of the first implementation of Quicksort was not by me, and I didn't collect any data about its performance. It was done by my supervisor, Pat Shackleton, when I was working for my first job in industry. Background is that he gave me shell sort as my next example program, which I wrote and delivered to the library of my company, software library. And when I showed it to him, I explained it and I said, I think I know a faster way of sorting than that. And Pat Shackleton said, I bet you sixpence that you didn't. And he lost his bet, but he never paid, except by actually implementing it on an old valve drum computer that was made by the same company. And those are the figures that are quoted in the original paper that Bob referred to. So I pass the credit to him, if I may.
Thank you, Tony. I'm afraid we lost Bob in the middle of that. First he froze, but now he's gone away altogether from the list of participants. So I guess he's trying to dial back in. Daniel, is yours a question directly to Bob? In which case, I think it would pay to stack it.
Yeah, I can ask it later. I was just curious about sort of randomized algorithms.
Let's hold it for later. Now, I've just got news in that Doug is about to join us.
Lovely.
But Sebastian, if you would, I think I'd actually like you to kick off and then we can slowly bring Doug up to speed. Would that be okay?
Both is fine, yeah.
Okay, so the floor is yours. Oh, no, I should introduce you. I apologize. Sebastian studied computer science at Kaiserslautern, then taught 2 years in Waterloo, Canada. He's now an assistant professor at University of Liverpool. His research focuses on space-efficient data structures and the analysis of algorithms. His Springer book on algorithms is in its 2nd edition. Over to you.
Yeah, thanks a lot. Can you see the slides?
Yes.
Okay, great. I thought I'd talk a little bit about the quicksorts of the 21st century, because after all, these are the only ones I had any part in. I'll do a little bit of a deep dive into, on one side, the multi-way partitioning, and on the other hand, one more recent addition to this Quicksort-inspired family, based on joint work with the listed people, Stefan Edelkamp, Conrado Martinez, Markus Nebel, Ralf Neininger, and Armin Weiss. I want to give a little bit of context and then go through some detail of this dual pivot quicksort, and then, well, won't say much about the rest for now. The context is something that Bob has brought up in his talk as well, and I used the same term, algorithm science, to highlight this problem that I see, that algorithms has a bit of a divide between works that are mostly empirical, that try to squeeze the most performance out of a specific application. And that's totally legitimate, but it's generally hard to get these results reproducible. And it's sometimes questionable if they generalize to other scenarios. On the other hand, we have the theory of algorithms, which focuses on these big O statements that, as we heard from Bob, don't really carry a predictive value. It's hard to attach a number. How long will this algorithm take on a certain input size if I don't specify any of these hidden constants? So, well, a bit provocative, you can say it doesn't help anything if you want to predict actual time. So what I'd like to see instead is what I phrase platform independent performance guarantees. So you have some simple model of reality that's still analyzable, but is useful in a prediction and still reflects the core elements of what is happening in a computer. You'll see examples of that later in the context of Quicksort. As a bigger case study for this approach to algorithms, I looked at all the sorting methods in the Java library. And there's two reasons for that. One is that Java is really, really widely used. So it's important to analyze these algorithms. It's also convenient that Java, unlike other languages, has a reference implementation of its standard library. So you can really talk about the implementation in the library as opposed to the GNU implementation of C++, et cetera, et cetera. And what's exciting from an algorithms perspective is that all the sorting algorithms in Java have been replaced fairly recently, at least within this millennium. And I say all algorithms, it is precisely two, but still they're both new. One is dual pivot quicksort that I will talk about in detail. It started as a hobby project by this guy, Vladimir Yaroslavsky, a developer at Sun Microsystems at the time, even though he has moved on since then. The second algorithm is TimSort, a variant of merge sort that is interesting because it is stable and it is adaptive, which means it tries to perform better when the input is at least partially sorted already. But today is Quicksort's big day. So let's not talk about this right-hand side. There's a very nice story from verification about this algorithm that I guess many people in this audience will know about. I will not touch on it, but if you don't know it, then Google for it. It's an interesting story and a nice laugh. Both of these algorithms come from developers as opposed to algorithms researchers at a university or from academia, which also meant that their focus was more on benchmarks and unit tests than on formal proofs of correctness or on the mathematical analysis of algorithms. And that's fortunate for a starting PhD student, because then there's lots of work to do on this. Why would you, I said Java replaced all these sorting algorithms. Why would you do that? In particular, programming library maintainers are usually very conservative because they're always afraid of breaking existing code. So why would you retire a well-tested sorting method in the first place? And I noticed in this context, I refer to this previous implementation just as standard quicksort because it's the only thing I knew when I started with this. That was already the state, and it had been like this for over a decade. So by standard quicksort, I mean essentially what is in Tony's original paper plus a few twists that were added later on and that Bob analyzed in detail in his thesis, and that Doug McIlroy and John Bentley polished to the final state for the C library. That was basically what was also used in Java until this magic year, 2009. And then Java 7 came along with this dual pivot quicksort, and the result was just that this is around 20% faster on random permutations. That clearly answers the question why they wanted to retire the old method. That's an improvement in performance that you can hardly ignore. When I first saw this, I thought, all right, maybe this is clever tricks in the implementation that somehow get the twist a little bit better than what was done before. In this case, this is not the explanation. I took the library code for both and extracted the core algorithms, like the code you would show in an algorithms class or in a textbook. If you take away all these extra bells and whistles, you still see an improvement. And it's interesting to see that the Java library before was actually slower, but that is because I'm only looking at random permutations, so that is a little bit unfair. But at the time, there was no sound explanation for what happened, why this was the case. Maybe it's an artifact of Java, but that seems refuted by now. And also, why did no one come up with this earlier? After all, Quicksort has been studied so much. Why is there something new to be discovered after 50 years of its existence? And I will try to give an answer to that today. So I hope you're curious now to learn what this dual pivot quicksort is. Here's an overview of what Quicksort works like. I feel for the audience today, I don't really have to go through this in detail. Just for the notation, I call this the pivot element. That's the element we partition around, and then we get two classes, the elements smaller and larger. And then there's this partitioning step that rearranges the elements according to class, small ones on the left, large ones on the right, pivot in the middle, and then we can recurse. Dual pivot quicksort does the same, except that it uses two pivots, produces three classes, partitions into three subproblems, and recurses thrice, not twice. And this is also what Tony pointed out before. This task of rearranging elements into three segments is something that Edsger Dijkstra posed as a programming exercise a long time ago as the Dutch national flag problem. And indeed, the crux of the matter also for dual pivot quicksort is how to implement this step efficiently and in place. We don't want to use extra space. That is one of the big qualities of Quicksort in general, that it can run without significant extra space. And that is something we want to keep. The core innovation, therefore, in this new method, I call it YBB algorithm or YBB Quicksort for Jaroslavsky, Bentley, and Bloch, because the later two also had significant influence on the writing of the library. So this partitioning method is the core innovation of this algorithm. And I want to briefly show on an example how it works. There's also the full code on the right for this quicksort, the core version of the algorithm, which is it's not too complicated. It fits on one slide. But let's instead look at the example. There's 3 pointers that will separate the 3 segments. And we start with this green one, K. And for the green pointer, we use this left partition, this left classification tree. So we start comparing with a small pivot, then with a big one if needed. And in this case, we find it's a medium element. And these can just stay where they are. And K moves one step on. Now we do this another time. If we find a small element, like in this case, then we swap it to the left. And thereby we maintain this invariant that everything to the left is small, everything to the left of K, but right of L is medium, and everything to the right of G is large, but there is nothing at the moment. We continue with K, and if we find a large element, this is similar to the original quicksort, we pass control to the other pointer and leave that element alone for the moment. So that element now, we start classifying on this element. And here we use this blue classification tree. That's the trick. If it's a large element, we can leave it where it is. If it's one of the other cases, we have to move it to the other side. And so in this case, we do this triple swap to get all the elements in the right position and move all the pointers forward. And one more time, then we notice that K and G are on the same spot. So partitioning has finished because we reached the point where they meet. And that's the final state of the array after partitioning. What's left is swap the pivots in place and recurse, but that is as you would expect. I want to give a little brief glimpse into the average case analysis of this algorithm, because that is where something interesting happens. I want to count comparisons for now, so just the key comparisons. And I only want to look at the first partitioning step. That is the core of the problem. How many comparisons do you need for a single partitioning step? And let's further simplify how many comparisons for a single element to classify. Well, that can either be 2 if it's in one of these 2 cases below here, or it's 1 if we're lucky and 1 comparison sufficed. How many on average? Let's try to analyze this. Say we first compare with the small pivots, and the other case is essentially symmetric. So then we have a cheap class if the element is small, and we need 2 comparisons otherwise. If we're picking random pivots, we can expect 1/3 of each type on average. So that average is out to 5/3 comparisons to classify 1 element. Now that sounds quite plausible, and it seems to work for the green and for the blue part because it's all nice and symmetric. Unfortunately, it's wrong, and it gives the wrong result. And the intuition behind why is there are correlations happening. We don't use this green and blue part independently of what is in the array. That is triggered by how many elements of a different type we find. In particular, if there are many small elements, then also the green range gets bigger because we keep moving with this green pointer for longer. And vice versa, if we have many large elements, the blue range is automatically getting bigger. And then again, we have more of these cheap classifications. So we can expect to have more than 1/3 cheap cases. And how many exactly? That is where the mathematical analysis of algorithms comes into the game here. For today, I'll leave it with the flurry of colorful pictures here. The key insight is assume you're sorting uniform reals between 0 and 1. And then everything can be reduced to studying known distributions, random distributions, and their expectation. I want to sweep this under the rug for today and just straight jump to the results that come out of that analysis. So here are our 2 competitors, the dual pivot quicksort from Java 7 and onwards, and standard quicksort, the tested veteran. And if we look at the number of comparisons, ta-da, we see there is a reduction by 5% from using this sophisticated new partitioning method, or the sophisticated new solution for the Dutch national flag problem. But then remember, algorithm science, there's not only comparisons that are happening inside the CPU and in the computers. Let's also look at other operations. I used right excesses, not swaps, because we're not necessarily using swaps in this triple rotation, but that's a minor detail. But you see, dual pivot quicksort doesn't shine here. I also went through the process of counting for the Java implementations, the exact number of Java bytecode instructions, the assembly language of Java, if you like. And again, doesn't look like dual pivot quicksort really helps. Then we thought maybe it's something to do with modern architectures. So we looked at branch mispredictions, and it turns out you can compute the exact expected number of branch mispredictions in a certain simplified model of how this branch prediction works. You find interesting results with precise constants involving pi and so on. But again, if anything, then dual pivot quicksort doesn't really improve here. So you might wonder what is going on. These 5% in the comparisons don't seem to really explain what is happening. And the answer is, as you might have guessed, all the cost measures I've looked at so far are happening inside the CPU, but we have to get the data there as well. And that is where the difference comes from. Let's look at some historic data. You can compute from some benchmarks. Here is one. A specific benchmark that has historic data for CPU speed and memory bandwidth. What the picture shows is the ratio, speed divided by bandwidth. And you can get some average growth rates per year. And you can get a regression line through that plot. And what that shows is this imbalance between speed and bandwidth, CPU speed and bandwidth is growing exponentially, right? This is a logarithmic plot. And so if you look back to the point in time when Doug and John Bentley were implementing the C library version, maybe it was that one instruction inside the CPU was roughly worth, one memory transfer was roughly worth 7 instructions inside the CPU. But when Vladimir looked at this problem again, it tilted to 30 instructions. So you nowadays have to take bandwidth into account much more than it was before. And so we have a last line to fill here, essentially the number of memory transfers. And here you see the significant reduction happens in this row and only happens in this row. So to wrap up this section, memory transfers are the only convincing explanation of why splitting into 3 segments around 2 pivots is helpful. And why was that not discovered earlier? Probably just because it wasn't faster when it was last examined in detail. Machines have changed, and so the algorithms have to change with them. That's the answer. In hindsight, it's a fairly simple explanation. It's just about the memory transfers. But it's quite interesting that even for sorting, this plays such an important role nowadays. A natural question is if 2 pivots help, maybe more pivots help even more. And this is what I spend a lot of time on in my thesis. You can generalize Quicksort in various ways. And in a sense, you get a unified analysis of all interesting variants of Quicksort with an arbitrary number of pivots. For today, let's cut the story very short. Comparisons are not really improved by using more pivots, but these memory transfers, again, you can see a significant improvement. There's a counterbalancing effect. If you use more and more pivots, then the code gets really unwieldy and lengthy. So you likely want to stay somewhere in a very low, small, single-digit number of pivots. I think the question is, can someone beat Vladimir's code of getting all this embedded into a robust library implementation? And so far, the answer is no. But this doesn't mean it's not possible. That's the end of this first part about dual pivot quicksort. I now want to spend a few more minutes on a more recent topic that may also convince you that Quicksort still poses new challenges and has new inspiration to give. And that is this Quicksort plus X. The picture might indicate where this is going, but we'll get there. The question to start at the beginning is maybe, why do anything different than Quicksort? Bob convinced you that Quicksort is still the best choice in most of the cases. I just told you that Java also uses Quicksort still, so why do anything else? If you're sorting relatively cheap, simple objects, where comparisons don't cost a lot of time, then this is true. Quicksort is hard to beat, and maybe memory transfers have to be taken into account. If comparisons are very expensive, then Quicksort is a known constant factor off from optimal. Even though it's a small factor, it is a significant additional cost if the list is big. And there's other options that do better on comparisons in isolation. Most prominently, heap sort and merge sort from the simple sorting methods. Heap sort has the problem in practice that it uses random accesses scattered over the array, and that slows it down significantly unless the input is very small and fits in cache. The other option is merge sort, which is great in terms of comparisons, but it needs a linear size buffer unless you get into in-place merging, which usually then again is slower in practice again. So we don't seem to have a good alternative to Quicksort, even if comparisons are more expensive. But maybe Quicksort can help us here. And I want to show you that the answer is yes, Quicksort can help by introducing this quick X sort. So this is Quicksort together with some other sorting method X. Conceptually, this is a very simple idea. We start as in Quicksort. We first choose a pivot. We partition around this pivot, so we split as before. But then instead of recursing on both subproblems, we sort one of the subproblems with this other sorting method X and only recurse on one side. That's a fairly simple idea. You might just ask yourself, why would I want to do that? Why can't I just use X instead if X is better than Quicksort, or stay with Quicksort? The trick is that when you're using X to sort this part, you can use the other segment, the other half of the array, as buffer area. So you get an out-of-place algorithm X and turn it into an in-place algorithm by using the other part of the array as buffer space. And as I indicated before, merge sort is great for the number of comparisons it does, but it needs extra space, so that's the natural candidate to use as X in quick Xsort. And the hope is we can inherit the good comparison count, but work in place. Now, again, this is an analysis challenge that lies behind this. It's a promise that we inherit this good comparison count, but it's not a given. Before I get briefly to the results for that, I want to convince you that you can actually do merge sort without destroying the other half of the array. So let's suppose this is the part that we try to sort with merge sort, and this is the other segment that we're eventually sorting recursively with quick merge sort, but is at the moment a buffer area. All we have to do is, so we recursively sorted one half, recursively sorted the second half. Now we want to merge. That is the point where we need the extra space. So what we do is just whenever we write things in merge sort, in merge, we now do a swap. That is the only real change. We first swap one of the runs to the buffer area, and then we merge back, taking the smaller of each and then swapping it in that place. Take the smaller again, swap it over until everything is back into this range. Then the left part is sorted. This part still has all the original elements that used to be there, but they're randomly permuted. And OK, jumping to the results, the number of comparisons on average for this quick merge sort is C of n, which is the same as x of n, the comparisons that this method X used, plus some linear extra term. We pay of the order n extra comparisons, and the constant in front of n that I call the quick Xsort penalty can be precisely analyzed. And it turns out for random pivots, it is 0.9. If you take median of 3, it gets less than half, 0.4, etc. And in the limit, it vanishes completely. So we rediscover an old wisdom from Quicksort. A small sample helps a lot, and is usually not worth going to a growing sample size. The number of comparisons of quick merge sort is also close to optimal. In particular, the leading term, the n log n term is optimal. The running time in practice, we did extensive experiments with this method, and unlike in-place merge sort and all these variants, it is very competitive to other options, even competitive to merge sort, which uses extra space. But we get in place without using extra space with very little overhead. That brings me to the end of my talk. So I just want to briefly say what I told you again, what I told you before. We've seen asymmetries in this new YBB partitioning method, the three-way partitioning method. That saves a few comparisons, but really the big story is use multi-way quicksorts if memory transfers become an issue, and they probably become an issue if your comparisons are cheap. If comparisons are expensive, you might want to look into some other tricks like quick merge sorts, and Quicksort still inspires new ideas here. I have a lot more to say about Quicksort, but like Bob, this is the limiting distributions for dual pivot Quicksort, because you brought that up. I wanted to remark on that. I'll leave it with that for today, and finish with the probably nicest explanation of how Quicksort works using not a single word.
Thank you very much, Sebastian. There's some great insights there. Technically, we're almost out of discussion time, but since it's running up to the break, I think we should take a few questions. There's one already in from Andre. I don't know whether you can see it in the chat.
I can open it now, but I didn't dare to disturb the laptop.
No, probably very wise. I can read it if you want.
Yeah, it's probably better. It's a bit slow.
Why isn't the net increase in the right memory accesses affecting the performance of YBB?
Essentially because they're in cache. Writes to the cache are not as expensive. So what I showed in this second line, maybe I'll briefly go back to that, was really the write accesses only. And that is, okay, we have to click through a lot of slides to get there. So this is the number of times you write to this array, but most of these writes are actually in cache because you just read the element there before. So you can write the same spot many times. That doesn't really cost in practice. What is expensive is bringing new data into the cache.
Okay. Are there any other quick questions? We'll have a break now, and there can be breakout rooms where you can discuss with individual speakers.
I'll answer the one about two pivot partitioning and equal keys. It automatically handles a lot of the problem with equal keys, because if there's a lot of equal keys, they're going to be either trapped between the two partitioning elements, or the two partitioning elements will be equal, and the problem is handled automatically. I think that's another reason why this algorithm does well in the benchmarks, because the benchmarks must have cases where there are lots of equal keys.
Andre, do you want to pose your other question verbally, or?
I think that was the other question.
Ah, fine. Okay. Okay, so we should now take a break of half an hour. Doug is, I'm pleased to say, there, and Doug will speak straight after the break, and then we'll have the question session with Tony. I think the Gemma from INI is going to create some breakout rooms, and you can elect which breakout room you go to. Don't burn up all the interesting items with Tony over the break.
So I'm going to pause the recording, Cliff, and actually I will create the breakout rooms, and we can.
Yeah, they should be on there. You should just be able to open them. There are 3, but yeah, feel free to make however many you want.
Yeah, so I think Gemma, people can join whichever breakout room they prefer. Okay, yeah. So I'll go ahead and pause the recording for now.
Okay. Right, the next talk is from Doug McIlroy. Doug told me that he's been writing programs since 1953. I doubt there are many people who can predate that. I also believe he's the only person to have published one of these CACM algorithms written in PL1. He may not wish to remember that. Doug's got a bachelor's degree in engineering physics from Cornell, a PhD in maths from MIT. Most of his career was with Bell Labs, where one recurring theme of his work, stream processing, led to Unix's famous pipes. Doug retired and became an adjunct professor at Dartmouth. So over to you, Doug.
I apologize for my mistake about what time this affair took place. It was not a time zone error. It was just misreading the schedule. You can see I've given a different title than what's been announced. I think it's more fairly represents what I have to say. I probably won't say anything that's a surprise to this crowd, but I hope to remind you that we all fall into traps, and Quicksort is full of them. Back when Doug Eastwood and I were putting macros into the assembly language for the 704, we had a curious side effect. Turns out macros can fill up the symbol table very fast with many new symbols per line of code. And the symbol table sorting happened between the two passes, and this suddenly went out of control. Eastwood fixed it. He saw a nice article in the JACM about radix sort. He put that in place of the quadratic sort, and all our problems were solved. Radix exchange. Oh, phew. Radix exchange is quite like Quicksort in that it splits the data recursively, but splits it first on the top bit, which is shown in and the split bits here are shown in boldface, which means that if you regard the keys as binary fractions, it's splitting at 1/2, and then it splits on the second bit, which is splits at 1/4 and 3/4, and so on recursively. The only trouble with this is that the splits are not adaptive. If you have a lot of small integers stored in large machine words, you spend all your time splitting on zeros until you get to the interesting data. Quicksort came along and it was adaptive. The hope is that you could split, things would be really good if you could split on the median of the bin, of every bin. And Quicksort gives you a good chance of splitting on the median. However, radix exchange has the benefit that it looks at every bit just once. Quicksort may look at them a lot of times, but it looks at them in parallel thanks to machine instructions that compare integers rather than look at bits. If it weren't for that parallelizing in Quicksort, we would scarcely care about the information theoretical lower bound on comparisons. We would instead only be interested in the volumetric bound on sorting. Quicksort meets the volumetric bound. radix exchange meets the volumetric bound. Quicksort doesn't. And yet it's a winner in practice. And Tony Hoare was justifiably proud of this invention. This is what he concluded his original Quicksort paper with. But as everybody knows, Quicksort has an Achilles heel. The worst case is order n squared. It's believed to be a very low probability of event, but an event that could be a disaster, perhaps missing a critical deadline, or producing garbage as a result of stack overflow. And in fact, we don't have to look back far for a worst case. A list of n equal keys is as bad as you can get. Or so is a list with few keys and many of each. In fact, that latter example caused Berkeley early on to improve its Quicksort program. But this was just the first of an ongoing whack-a-mole exercise in overcoming simple counterexamples to Quicksort. The easy fix for these two errors is simply let's go back. There's an easy fix for these duplicate errors. Oh, wow. I better get back to the beginning somehow.
Oh, you're not too many
Okay,
slides.
here we go. Here we go. Here's in the real world, most quicksorts are in fact use two-way splits, and three-way splits are the answer to duplicate data. And three-way splits take more comparisons nowadays. You compare for inequality and then for equality. But I remember back when Quicksort was, back when Fortran was invented, the only conditional in Fortran was the three-way if statement. But since then, and the three-way if statement actually had a machine language equivalent. It branched on equal, less than equal, or greater, less than and greater than. But since then, Folklore has reduced our machines not to have three-way branches. The Folklore is that conditional must be Boolean. That's a two-way. There's no reason for putting that in hardware, but this has discouraged people from using three-way splits in Quicksort. It slows the inner loop. Now, in the original Quicksort, Tony said split on a random element. That idea has disappeared. Very soon after Quicksort was published, something called Quicksort appeared in the literature. It split on the middle element of the array. And it touted its advantage as it didn't need random numbers. Now, Tony's n log n claim is true if you use random splits. However, if you translate that into two-way, if you translate that into a deterministic routine, it's equivalent to saying, oh, the input is random. That's simply a way of saying unpredictable. The most unpredictable input is independent, identically distributed. So every time you write deterministic Quicksort routine, you are buying into the assumption that all data are independent, identically distributed in order to get your n log n time estimate. Oh, I keep hitting the wrong key here. Those quadratic behaviors are unavoidable. And although no matter how many of the cases like all equal keys or pre-ordered data you kill with a whack-a-mole, there are more left to find. I wrote a little program once which would, by bugging the comparison routine, which is often a parameter of a generalized sort program, by bugging the comparison routine to generate the array on the fly. Every time a comparison to a previously unvisited element is made, you simply assign that element a higher value than the previous one. And here is, in fact, the array that an ordinary binary splitting Quicksort, one that it was indeed found in the wild. This is a counterexample found by this technique. That's just one counterexample, as somebody once told me when I argued that a paper should be rejected. But you can create more counterexamples at will simply by salting the array with a few values before you apply this bugged comparison routine. people have looked for ways to increase the probability of picking near the median. And so we try medians of 3 and so on. And a pick of 3 random samples would be even better. But the order n squared bugaboo remains. The C++ library definition of the sort routine actually requires it to be an order n log n. It actually rules out Quicksort as a candidate for the standard sort routine in C++. But by and large, there hasn't been much public outcry against Quicksort as the default standard. Bob Morris, who was chief scientist at the National Computer Security Center, liked to say this. Is my screen badly shared again?
So Doug, could you put
Doug,
it into slideshow?
Is my screen badly shared again?
You need to go back to slideshow, Doug, if you're satisfied where you are in the sequence of slides.
Oh, that's what happened. I fell out of the slideshow. There we go. Bob Morris said this. He was mocking the agency's tendency to equate verified software with trusted software. And I think he was deliberately trying to rattle cages with it. Quicksort isn't malevolent like the security stuff that Bob Morris was concerned about. And it's been verified. But it's been verified, so it ought to be trusted, but it cannot be trusted not to go quadratic. Another bit of folklore that pervades is that Quicksort runs in time n log n. Not only does it suffer from the possibility of running in time n squared, I should have said having n squared comparisons. Comparisons may not be O of 1. And that's another bugaboo of Quicksort. If you feed it string data, the running time is not n log n. The running time is probably closer to somewhere between that and the much more generous volume estimate. When it was revealed that the Pentium produced wrong values for a few floating point divide problems, a public outcry caused the Pentium chip to be recalled. I haven't heard such outcry against Quicksort. In the case of Pentium, the manufacturer tried to say, well, it's a rare event, so we're not going to do anything about it. And that has been the attitude of when one puts Quicksort in as a standard sorting routine. Certainly the public needs to be aware of the problem. Maybe it should be solved in one of these ways. I'll leave it up to you to decide which, if any, is a good idea. What put it up front and center that Quicksort can bite you and has bitten many, despite the fact that the odds on the basis of the random assumption of any modest Quicksort run on, say, 1,000 values ever having gone quadratic, the odds are vanishingly small, but we know from experience the odds that it really can happen. But go back to the original Quicksort. Remember, it was randomized. All the Quicksorts that have their trouble, that we get troubles with, are non-random. If you had a genuine randomized Quicksort, and it suddenly ran at, say, 2 sigma away from its expected behavior, well, just start it again with more random values. That has very good chance of immunizing against quadratic behavior. So the real problem is that we're using deterministic Quicksorts. Tony's original didn't suffer that objection. Therefore, we can paraphrase what Tony said about Algol this way. His Quicksort is better than its deterministic descendants. Or yet another way to say it is a deterministic Quicksort is an oxymoron. At that, I'll leave it I'll stop and hope to hear brickbats from the audience.
Thank you, Doug. That was a provocative talk. Does anybody want to come back to Doug with comments or questions?
Yeah. I have a comment, Doug.
Yeah.
I recall, I think I've got this right. You having this really, rather than choosing the median as the pivot for Quicksort, we all immediately understand how it can mess up. But you had a really nice example of the median. I think it was the median of 3, the first, the last, and the middle element. So we should have been cranking, if they're random, we're cranking the number of comparisons down to about 1.2 n times log base 2 of n, 1.19 to be specific. Sorry, Sebastian. But I think your example that worked badly for the median of 3 was something like put the max in the middle and the first half is increasing order and the last half of decreasing order. Could you comment on that?
That is, I hope I didn't say that. That distribution is a nice counterexample for splitting on the middle value, which
Sorry,
is extreme.
No, you had it for the median of 3. I thought something.
In fact, I think I have indeed said that erroneously on occasion, but
I thought it was okay.
But
so
the really bad thing about this tent shaped distribution is that if you split on the middle value, you lose.
Clearly.
Speaking of things I've said before, in the Bentley McIlroy paper about Instead of using a median of 3, use a median of 3 medians of 3. We rejected the notion of using a random number generator for the reason that, quote, sort routine has no business side affecting the random number generator. But a little congruential random number generator is so small, you could just put it inside the quicksort routine. It would hardly make any, and it would work just fine.
Even better, you could
Probably we
separate out
rejected.
by randomizing the order before you even get to the sort.
That's if you do a random permutation, that's a fair thing to do too. And in fact, I think Tony's paper points that out. But turning a randomized algorithm just gratuitously into a non-randomized algorithm is a really bold and dangerous move.
Any further questions?
Yeah, I'll ask one. So, this, as you say, there's a kind of whack-a-mole aspect to this, and there's the no free lunch theorem, which says that, for any strategy, there's it's as bad as any other strategy. So, but this, using randomization as many speakers have suggested, it gives you the ability to actually defeat an adversary. The other strategy that one might use is adaptivity. That is, if you can recognize, what's happening, or you do learn something about the distribution that's being given to you, then perhaps you can adapt to a more effective strategy. So are these things where you can, you can imagine actually taking out your warning label so that you can say this does actually, it will work effectively in practice. No adversary is going to easily defeat it.
Well, I thought maybe I should thank Doug for confirming the views that I put forward so long ago, and just mention that at the time I realized that Quicksort must be one of the very few early algorithms that combined Monte Carlo methods and recursion in application to the fundamental problems of commercial computing. Thank you, Doug.
And apologies for using this affair as a learning experiment, as a learning opportunity for how to use Zoom.
Oh,
I need to do it more often.
yes, I expect I shall have it.
I'm usually on the receiving end of Zoom.
Same here. You have my sympathies.
Well, if there's nothing else burning, I think we can pick up other points during the more general discussion. And I'll move on to the final session of the day. Tony's kindly agreed to answer questions or involve himself in discussions with the other speakers and all of the participants. Of course, Tony needs absolutely no introduction to this audience, but I will point out he has an unusual background, which, as well as a degree in classical languages and ancient history, led on to qualifications in Russian and statistics. And both of those things have a connection with the first question I'm going to address to Tony. So he discovered Quicksort when he was in Moscow. And a very obvious first question for me to ask is, how did you get the idea of Quicksort? What were you trying to do at the time? And how did you record the idea of Quicksort at that point?
Right, thank you. Well, one morning in the spring of 1960, I was lounging on the sofa bed of my graduate digs on the Lenin Hills in Moscow State University, and I wondered about the problem of how to sort an array of words held in a segment of the main memory of a computer. In trying to write the program to solve this problem, the first idea that came into my head was a quadratic algorithm, which is now known as bubble sort, well known. Why was I doing this? Because I had just received a letter from the National Physical Laboratory offering me a very senior position as a senior scientific officer in the scientific civil service. And so I was looking into Russian attempts to do machine translations. It led to the fact that my first journal publication was in Russian and published in the journal Machiny Perevod, which means machine translation. Going back to bubble sort, in my thinking about sorting, I realized that this was quadratic, and wondered whether there was anything faster. And the first idea that came into my head was that the algorithm now called Quicksort. I could see fairly quickly that on average it was complexity n log n, particularly, but I was incapable of doing anything more scientific. I did use an information theoretic argument based on Stirling's approximation factorial, which showed that no sorting method could be faster than that on completely randomized data. I was attempting, it was interesting to inquire how it was that I made this transition between bubble sort and Quicksort. Must be some rational explanation, but I have no recollection of it. However, I can suggest a rational reconstruction of my possible insight. Both the algorithms partition the array. The bubble sort splits into two parts, A and C, and moves elements from C to A. And Quicksort uses three partitions, with B in the middle. And it moves elements of either C or A into the segment B. I think this maybe would satisfy Doug's comment about the conditional in the Fortran having the third case built in. So that's my explanation of how I actually came to invent Quicksort and why it happened in Moscow State University when I was spending a year in Kolmogorov's department of probability at the university. After doing my degree in statistics, or rather my qualification in statistics. So, do you have any further supplementary questions?
Well, I do have a further question, but I should invite other people to jump in.
Right, good. Happy with that.
So Tony, is there no truth to the story that it was inspired by learning about recursion in Algol 60?
Yes, I think part of Cliff's first question was, how did I propose to write the program that actually implemented my sorting ideas? And I did at that time, during my statistics course, I'd had a 1-week course from Leslie Fox in programming the Ferranti Mercury computer, which had just been delivered to the computing laboratory at Oxford. And so I thought of writing it in Mercury autocode. And I think I must have written the partition algorithm, which is not too difficult. But when it came to keeping a record of the partitions that were awaiting awaiting treatment, I couldn't manage it. And I thought, oh, well, there's something like that. But when I came back to Britain, I was employed not by NPL, but by a computer manufacturer, a small computer manufacturer, Elliott Brothers in London. And my second task there was my third task was to design a new programming language for a new computer called the 503, which was 60 times faster than the current computer sold by that division of the company, which was called the 803. And it was considered quite usual in those days. When you brought out a new computer, you brought out a new high-level language for it as well. But in the end, as a result of attending a course in Brighton, where I went with the managing director and the sales manager of the company, and on one of the programmers who for the last 60 years has been happily my wife. And coming home in the car, I said, well, why don't we just do Algol 60? And so I studied the manual for Algol 60, which happened to be in our company library, and found the famous sentence that introduced recursion into Algol 60. Well, I also read an issue of the communications of the ACM, how one uses a stack to implement recursion. And I realized that I had the solution to my coding problem. If I used recursion, everything would look very, very simple. And I think so it has been. It's certainly the way that I think of it.
Very nice vote for recursion and Algol. Sebastian has a question.
Thanks. Yeah, a very natural one. We've heard before that the 1962 paper took a lot of ideas already that were later developed further and sometimes rediscovered because people did not read the old paper. Except for one thing, which is dear to my heart, that's using several pivots. Have you ever thought of that early on? Was that something that you played with, or was that obvious that it doesn't help maybe at that time?
It didn't occur to me to pursue that. Something like it was introduced by Eske Dijkstra's Dutch national flag algorithm, which in the Dutch flag, there's a white space in the middle and a red, I've forgotten what it is now. Anyway, it was in three parts. Bax also had a very interesting algorithm called smooth sort, which ensured that when two keys were equal, that the order of the original input would be preserved. And I think smooth sort is really on the way to being a three partition sort, used effectively. And I should have picked that one out more quickly. That seemed a very good recommendation. But I think the three-way one, if you actually look at the simplicity of the program which implements it, you can see that it really deserves a place along with Quicksort and other versions of floating bear, which have the same sort of splitting techniques. So thank you. I will hope that I would like to support your view that a practical sorting algorithm is likely to be Quicksort plus X or Quicksort plus X plus Y, in the sense that certainly if you move away from Java, you find that the manufacturers are very keen on writing programs that are adapted to the particular computer on which they're run, the commonly based computer architectures. And really, those have become very, very standard now. And therefore, they choose an algorithm which is very runs best on machines with quite machine-dependent parameters of transition between one method and another. And that is perhaps a difference between the sort of Java community, which one might say includes the academics, and software manufacturers who are keen on the actually existing architectures and exploiting them to best advantage. Perhaps I'll come back to this later.
Tony?
Yes.
This is Jay.
Hello, Jay.
I have a standard question for students when they complete their PhD defense. What further work do you plan in this area? May I ask you the same question?
What kind of work do I plan in this area?
Yes, what kind of further work would you be doing on this problem?
Oh, I am very I'm just going to bow out the people who are made presentations at this virtual seminar. Seem to me to be doing a splendid job.
I didn't expect an answer from you. I just wanted a short laughter.
Warren, you have a question?
I have just an idea, and I don't know if it's being pursued. Very commonly used now in most architectures are 512-bit wide words that are used for a variety of data transformation operations, and they're either 8 64-bit numbers or 16 32-bit or whatever. But imagine that such an instruction in such an architecture that could sort 8 or 16 values and produce a vector of 8 or 16 values in a few clock cycles. I mean, and that's going, if you will, that's not the Java approach, but that's the manufacturer specific approach. I'm just curious if what your thoughts might be about the use of that, or anybody's thoughts, and whether or not some investment should be made there. Generally, those things though are aligned in a way that are 32-bit boundaries. So it's not, you would want to align your array to such boundaries and so on that you would be considering to sort. But any comments would be.
I would like to take that as an example of the kind of transition that you make in optimizing. That for numbers below a certain somewhat machine dependent, very machine dependent limits. I mean, so say up to hardly likely to be more than 10. You would clearly want to use that for all partitions that are less than 8 words long, say. And that would be an example of Quicksort plus X. That's a good question. I hope you like the answer.
Sure, it's great. Thanks.
Daniel?
So this is actually sort of a generalization of that, right? So hardware tends to sort of limit to some extent what you can efficiently do in software. Are there capabilities that you wish were baked into hardware that you think would help with algorithm design and performance?
Oh, unfortunately, hardware seems to be going in the wrong direction. It's getting more and more complicated if you want the really top speeds, because your programs have to not only work abstractly, but implement the ideas on things, strange hardware devices which are designed for other purposes. For example, graphics processing units, for example, are a case in point where you've just got to respect some very clever matrix algorithms working on fixed size matrices, and you want to exploit that. You need a lot more skill in software, in addition to the skill that you have in actually using the results that they will give you. Nice question, yes. So on the whole, I don't ask hardware people to do anything too much, because they will take things that are that make their chips look better, rather than are actually easier to use. Software gets the thick end of the brush when dealing with hardware designers. They tend to win and cause more problems. Oh, any hardware designers in the audience? Well, I exaggerate, of course.
I hesitate to say anything, having worked on 5 or so microprocessor designs over the years.
Oh, yes.
So, what would you have a hardware designer say? I mean, essentially, they're trying to provide maximum resource at minimum energy.
Yes. And say good luck to you.
Yeah, but I mean, for instance, that's another question when you talk about these movements, though, that's critical as far as the energy. The way you partition when you have an embedded system is different, because you want to never leave the cache, for instance, and so you don't. I mean, there are all kinds of ways that these embedded systems do, I'll say, change Quicksort or whatever to increase their locality. To mitigate the movement of data from the processor to the main memory. And so And of course, that can speed things along too. And I think many people are savvy to that, but it can be an extreme issue in for handheld or battery operated devices. And so just generally having an ability in your programming language to talk about your resources and where they are would be of great benefit to those embedded
I think this is another case of Quicksort plus X plus Y. And the Y might be something, might have to be expressed in a language that gives direct access to the relaxed memory. So you would have people optimize the the final, whatever it is, 16 or more, to fit the to make sure that the relaxed memory is going to be fully exploited, setting up, as it were, the causal chains which the relaxed memory then uses to schedule the individual instructions of the program. Yes, any more examples of X plus Y? Well, there's TimSort, which is better for particular kinds of applications where there's some reason to suppose that fairly large chunks are going to be pretty well sorted already. And using the curious buffering technique that we've just had described to us, which I'm afraid I didn't quite follow, the overhead of the merge sorting, which is the basis of the TimSort, seems to be, one seems to be able to control that.
Well, another X plus Y might be the string version of Quicksort, hybrid between Quicksort and radix sort that Bob Sedgewick and John Bentley wrote about, which in fact exploits an idea in your original Quicksort paper.
Right.
If you were sorting long things, it was silly to keep sorting on the high order, to keep looking at the already sorted high order parts.
Yeah. So radix sort is well on the cards for very reasonable word lengths. I think that I like to think of perhaps the most common use of sorting by the consumer of software is to sort change the ordering of the columns of a big array. So if you have you see it I use it mostly in Outlook, where you start with sorting things by time, and within that you may, whenever you wish, press the head of another column and get it sorted by that column. So the user himself decides what the order of the eventual sort should be by choosing what the priority, as it were, of that ordering is in the current display given by a program like Outlook. And there, I think you'll automatically get the user actually wanting to specify what the radices should be. And there it is very important to have a smooth sort so that you don't change the ordering of the other columns when you change the ordering of this column. And so the smooth sort and its perhaps its extension to a 3-partition element, Dutch national flag, are also very much on the cards.
In practice, maybe you would deal with that just by putting sequence numbers on the records. Then they're not equal, and then also the smooth sort happens automatically.
Thank you.
Maybe a remark on this is, if you would ask me what is the left open problem in sorting, I would say it's sorting in place and stable and fast in practice.
Yep.
If you leave any of the 3 out, I can point to a solution, but if you require all 3 of them at the same time, stable, in place, and fast in practice, fairly competitive to other methods, that seems challenging.
In place, I think I would have to think about that a little bit longer than I can manage online, as it were. Thank you.
People have been thinking about it for 60 years.
Yes, yes. Or perhaps I should just say, I leave that to you.
That might be a very good point for the chairman to step in and close by putting another question to Tony. So Jay's question about do you plan to do further work in this area? Of course, Tony has done further work in a number of other areas as well, notably verification. And I wonder, Tony, if you have any feeling of lessons that you can take from the discussion and the 60 years of research about sorting for the subject of the rest of this week, which is the Verified Software Initiative.
I think that's yes. That's I need to think a little bit. I think perhaps it comes from the quicksort plus X plus Y, that X and Y may be rival theories of how one can best sort, and come from different research communities. And it might benefit by considering the possibility of the use of the X plus Y technology, and we must use the interoperation of technologies which may have started off as competing in the design of tool chains, for example, for in the life cycle of software products, and ensuring that the same tools which are available for standard languages or general purpose languages can be used for a range of programming languages which have hitherto been regarded as academic competitors. So in the next phase of the Verified Software Initiative, I would hope that our theories and tools will even support heterogeneous programs. These are programs with components written in different languages, each specialized to some particular purpose. Important examples of heterogeneity are hybrid systems, or now known as cyber-physical systems. Typically, these contain components requiring access to special purpose hardware, which I've already described, field programmable gate arrays or relaxed memories. And other examples of heterogeneous programs arise in company-wide data processing systems, which have components written for particular purposes like spreadsheet languages or data retrieval utilities or scripting languages, which are used for particular parts of most large commercial systems, programs. So I would draw the conclusion or summarize the conclusion in the term unifying theories, which is something to which I've given quite a lot of subsequent research in very fruitful collaboration with my long-term research colleague He Jifeng, or Jifeng He, Chinese academician now, and Jim Woodcock, who's been working in cyber physical systems and developing ideas, and actually for particular applications, for particular commercial applications, developing programs in which contain components, highly heterogeneous programs, and working out the theories which are common to them all, and thereby giving the eventual deliverer of the complete system confidence in the correctness of the components, which have been very often contributed by multiple subcontractors. Because without some assurance, the primary contractor for the complete project just cannot stand the risk that the components will not behave in a manner that is understood by the main program, which is running the whole show. So I think he had a very good reason to specialize in unifying theories of programming. And of course, it does use, this is the example that I would give, where we want a common theory of ordering. We need a common theory of ordering when we incorporate interworking of different sort algorithms. And though that's why I think it's a good thing for us that this particular session has been included on the initial day of the virtual seminar of verified software in the INI VSI program. Good luck to those who come after.
Well, and you've created the perfect link to tomorrow's talks on hybrid systems. So I think with such a neat connection, we should probably end there and stick roughly to schedule. And thank you, Tony, very much. And of course, the other speakers and all of the participants.
Thank you all. Yes, I shall leave. Shall I leave first? Bye.
Thank you. Great session.